Hello, I'm Tyler Wycoff, and I'm joined by Sebastian and Victor to give this presentation on turbo machines. The basic concept is that you have a machine that adds or removes energy from fluids. It does this using rotors on a shaft. If it's applying energy to the fluid, it is a pump. If it's removing energy from the fluid, then it is a turbine. The illustration on the right shows the basic idea. A turbine has fluid come in, it moves the shaft, energy is extracted, fluid exits. While in chemical engineering, we're a lot of times going to think about the big industrial applications of turbines and pumps on the left, it's helpful for understanding turbo machines to have the idea of everyday turbo machines, such as a ceiling fan or something like a garbage disposal. So it's important to know how exactly these are feasible on an energy level. So if you look at the top right graphic, you can see that we have fluid coming in perpendicular to a blade. So for our pump down on the left, we have these energy triangles, which is a combination of the apparent velocity of the fluid, actual velocity of fluid, and the velocity of the blade. The velocity of the fluid coming in is totally perpendicular to the blade. And as it exits, the velocity is no longer perpendicular to the blade, meaning that it has been pushed by the blade in some way and energy has been imparted. In an opposite argument for the turbines, we can see in the same way that the velocity comes in perpendicular. It's no longer perpendicular when it exits. So a force must have acted in the equal and opposite direction to change on velocity, which is in the direction of blade motion. So energy has been imparted on the blade. We can do a very simple energy balance to get the work done. We have the change in kinetic energy, which is 1/2 the mass flow rate times the change in the velocity squared. The change in velocity squared here is the sum of the change in velocity squared of each of the components of the velocity triangle, which gives us this formula at the bottom for work done by a turbine or pump. We can also look at it from an angular momentum balances perspective. We already covered momentum starting from before quiz 1, and we've refined it all the way up to chapter 5, where we got this first equation here. And then if we only consider velocity in the theta direction, and we only consider net flows, then we end up with the Euler turbo machine equation here, which is very important for analyzing them. And if we multiply both sides by omega, it gives a simple formula for work in terms of blade velocity and the angular velocities going in and out of the turbine.
So the first thing I want to talk about is pumps. And as previously stated, the basic idea beyond the pump is to increase the pressure of fluid via the addition of energy using a shaft with rotors. Each blade on the impeller will accelerate the inflowing fluid particles, which will then be pushed radially towards the casing, thanks to centrifugal action. So that's from the inflow to the eye to what the casing is on the figure on the left. As the fluid gets pushed into the casing, the velocity itself is going to be forced to decrease. However, thanks to conservation of energy, this decrease in kinetic energy will be converted into pressure, at which point the fluid will be discharged. And that's the whole point of the pump. Next slide, please. A few more basic characteristics of pumps like these. To the right, we have images of actual impellers. The impeller A is open, while impeller B is closed. And here you can see the mounted blades that are responsible for centrifugally pushing the fluid out towards the casing radially from the eye. Impellers can be mounted sequentially on like the same shaft to achieve a continued increase in pressure. These are called multi-stage pumps, so you can get large increases in pressure this way. They're also not limited to fluid inflow from only one direction. A impeller with inflow from both directions, at like the eye, is a double suction impeller, and hence a double suction pump. Next slide, please. Here's some comments on pump performance. Like predicting the actual performance of a pump system is really difficult because it's a 3D turbulent system. In practice, we have something called pump performance curves, which graph relevant details like flow rates, head loss, efficiency, and these are usually provided by the manufacturer to the engineer, and we use those to like get the job done. In terms of efficiency, we have this expression right here, which is basically saying that efficiency is measured as a fraction of power that's actually transferred into the fluid from the rotors. And there are sometimes 3 reasons that we can have efficiency loss. There are mechanical losses, hydraulic losses, and volumetric losses. Next slide, please. Yeah, we have a real world concern here when it comes to operating pumps, that the phenomenon of cavitation. So what that is, if at any point the pressure in the system gets low enough to the point where it matches the vapor pressure of the fluid, bubbles will start to form, which will damage the pump components and decrease the efficiency of the pump system itself. It's really bad. So there's a lot of complicated math involved, but basically, you have a net positive suction head value provided by the manufacturer usually because it's determined experimentally, and it's called NPSHR. And we have a experimentally determined, a theoretically determined value called NPSHA. And as long as this value is greater than the R value, the required value, then we can avoid cavitation, and the expression is right there. Next slide, please. Now we have axial flow pumps. So optimal operating conditions for centrifugal flow pumps are usually applicable when the NSD, which is a specific speed dimensionless value. So it's like the operating speed of the pump is less than 4,000. For some applications such as irrigation or other things that are a very high flow rate is required, this is not like optimal. So in axial flow pumps, fluid flow is driven by the tangential force applied by the rotor blades on the fluid. As opposed to centrifugal action, we can see the rotor blades in the diagram on the right, and you can achieve NSD values in these axial flow pumps over 9,000. If you want something more in the middle range, for middle range applications, you have mixed flow pumps, and these are the result of combining elements from centrifugal flow pumps and axial flow pumps, and these will give you NSD values between the 4,000 and 9,000 range. And on the next slide, we have a picture of a mixed flow pump example. As you can see, it's a little bit different from the other two.
So now we're going to be talking about examples of turbo machines. And the first example we're going to be talking about are fans, which operate at low rotation speeds, but can move large amounts of gas easily. And depending on the location of the fan, it can be classified as a blower, exhauster, or booster, all with different functions. And different fan designs include centrifugal, axial flow, and mixed flow fans. And they're often constructed with lightweight sheet metal. Next slide, please. Another example are turbines, which are devices that harness kinetic energy from fluids to produce usable electrical energy. A lot of these are wind turbines, hydro turbines, heat engines, and they're used in a variety of applications, and each turbine has a somewhat different design to do its function correctly. But the two main types are impulse and reaction. Next slide, please. The first type of turbine are the impulse turbine, which basically they change the direction of a fluid flow or a gas jet. The resulting impulse creates the turbine, lowering the fluid flow kinetic energy before exiting the turbine. There is no fluid pressure change in the turbine moving the blades. And also the blades are also all symmetrical. An example of this is the Peloton wheel, where like the water enters the turbine radially, exits axially, and produces electricity efficiently. This type of turbine is usually used in electrical generation in medium or large scale hydropower stations. Next slide, please. And then finally, the reaction turbine, which is this turbine basically has torque is generated by reaction turbines. By reacting to the pressure or mass of the gas or fluid, resulting in a change of pressure as it passes through the turbine rotor blades. The casing holds and guides the working fluid, as well as maintaining the suction transmitted by the draft tube and the hydraulic turbines. Therefore, the static pressure reduces across both the fixed and the moving blades. The velocities in the reaction turbine are often much lower, and the entering blade relative velocities are almost axial. Compared with impulse turbines, reaction turbines are much more efficient at higher speeds. And there's two types of reaction turbines. There's the Kaplan and the Francis. Now, the Kaplan turbine is evolved from the Francis turbine, as shown in the picture here. The Kaplan turbine works based on the principle of axial flow reaction, and the friction is much less within a Kaplan turbine. And then finally, this turbine efficiency for reaction turbines is the inverse of pump efficiency, meaning it's the ratio of the shaft power output to the power available in the flowing fluid. Next slide, please. These are our references. Thank you for listening to our presentation, and have a wonderful day.